Hi, this is a supplementary lecture for Week 8 on an Introduction to Queuing Theory, which is all about lines. Queuing theory was basically invented in also I believe this came as soon after the original stuff that was done in Bletchley Park, which is a war effort for the coding, where they try to figure out Enigma, the German Enigma machine and all that. Amazing. It's an amazing story that I would ask you to, I think you'd be very interested in checking it out. A lot of modern computing and mathematics comes out of that, and a lot of things that we can do today in business as a result of the people at Bletchley Park at least getting it started. All right, enough about that. What I wanted to say is queues are all around us. It's not just simply for people who work at banks or for people who are in call centers, but there are queues for phones. I just mentioned there are queues for call centers, for people who are waiting in line on the telephone. If you've ever been to an airport, you have to wait in line. If you've ever been to a hospital, you have to wait in line or wait in a room for labs or to see a doctor. So there's all kinds of stuff where we have to wait. And in fact, if you're on the internet, you're constantly waiting to be served, even if you don't know it. Lots of different places where there are lines. Queuing theory helps you understand from a high level, without having to model it in super duper detail, what are the different balances and trade-offs, and to get you in a ballpark about maybe how many servers you would need to be able to do something. It can really help you with capacity, understanding how to meet capacity, or minimize your capacity use by and at the same time meet certain customer expectations. So let's go through that in here. So after we do this, we'll be able to explain the fundamental aspects of queuing problems. I'm going to keep this fairly short so that I can show you how it works in the Excel spreadsheet that I developed for you. And it does use something called QTP, which stands for Queuing Tool Pack, which you have available on the from download on the site. It's a free Excel add-in. All right, and we'll use Excel to calculate the queuing parameters and explore some of the trade-offs between these. So first of all, what is it? So a queuing process involves arriving at a certain service facility and waiting in line. Okay. The queuing system is a set of servers and the rules that govern how the customers are processed or how the items are processed when they arrive. The characteristics that we're going to care about are the arrival pattern, particularly the distribution and how often people arrive in the particular queue. Like, do they arrive on average 1 per minute, or do they arrive on average 5 per minute? And is that arrival pattern exponential, or is it normal, or whatever? Second thing is the service pattern. Once somebody gets into a service, whether it's a customer enters into not just into the queue, but into a server from the queue, what is the typical pattern that happens there? Is it normal on average 6 minutes, or with a standard deviation of 1 minute, or is it something else? The third thing is the number of servers. How many servers do we actually have? Do we have 10? Do we have 2? Do we have 15? A fourth characteristic, and this is a little more minor, but it's definitely important, is the holding capacity of the facility. So if you can imagine this, if you have, say you do have a bank and you have people getting in line, at some point there's not going to be enough room to fit them. And also, you might think at some point they're going to start turning away. If the line gets so long, they'll just say, well, heck with this. I'm just going to do this online, or I'm going to go to a different location, or I'm going to come back on a different day or a different time. And then finally, the order in which the customers are processed. Is it first in, first out? Is it last in, first out? And that's called the queuing discipline. Examples of this would be people waiting in line at bank, phone calls waited, people waiting in line to be served at the hospital laboratory, etc., etc., etc. Okay. Now, queuing theory is a little bit in between. It's online with sort of statistical methods. Here it is right here. It's online with statistical methods and simulation. In some ways, it's more powerful than simulation because it lets you understand things from a high-level point of view, so you can do a lot of learning with it. but it's not as powerful in simulation as simulation is in terms of giving you an exact answer. So if you need an exact answer, modeling it in great detail and running a process simulation, which we don't cover in this class, that's covered in a second class or a separate class in Master Black Belt, or in a process simulation class that we have available. However, queuing theory, in my opinion, is more important and more fundamental than simulation because it allows you to kind of understand things, and it's a much better tool for design than simulation is at early stages of a design. Okay, so that's where it is, somewhere between the high certainty of knowledge like mathematical programming or cost-benefit requires, but less than that, but there's more information that's needed than, say, using game theory to do something where there's basically no information, you just use kind of mathematics and human nature. All right, and we already talked about these Q characteristics. There's a notation called Kendall's notation, which just essentially has slashes for these. So it says, what's the arrival pattern, what's the service pattern, what's the number of services, what's the capacity, and what's the Q discipline that we use. So for an example, here are the typical things for the inter-arrival time, which is the arrival pattern. If the inter-arrival time is deterministic, that is, we're just going to use an empirical distribution, we call it D. If it's exponentially distributed, we call it M, for some reason M. And the reason is because if it's Erlang distributed, we use E. If it's any other distribution, we use G. That's the typical notation. Now what I can tell you is that the most common of these, whoops, let me go back to my normal. The most common of these is the exponential distribution. So that's the most common that we use, and it's a great first cut. So we usually start out with an exponential distribution of arrival times. That means that they may arrive on average 1 time a minute, but that they could arrive as much as 5 in a single minute or as little as 0 in a minute, etc. Okay. Q discipline that we usually use is first in, first out, but here are a few other ones, etc. So for example, an exponentially distributed arrival with exponentially distributed service times, 5 servers and a capacity of 30 and a first in, first out queue would be MM530 FIFO. Okay? We're going to stick in this case with NK queues. All right? So we're going to assume exponential arrival pattern, exponential service pattern, and then we'll put in the number of servers and the size of the queue, and we're going to assume that it's first in, first out. Okay? By doing that, you can really get a lot of things done, and you can make some good. It's a pretty general one, and you can solve a lot of problems. So just to give you an idea, in an exercise, we have a new smartphone arrives for inspection exponentially and on average every 2.5 minutes. It's taken by a QC engineer on a first-come, first-served basis. There's 1 engineer on duty, and it takes an average of 3.5 minutes to inspect each smartphone. Service times are exponentially developed or distributed. We have an MM1, and the size of the queue is infinite, and it's first in, first out. It's a FIFO queue. Okay? Where the M here is 2.5 and the M here is 3.5. Okay, so this is the service time, this is the arrival pattern. Okay, not going to worry too much about that. By the way, if you do have MM1 with the infinite size of the queue and a FIFO queue, these are some of the solutions to the equations that we can have. Now, I'm not going to go through those. You can look them up on the internet, but already you can see they're getting fairly hairy. And believe me, when you go to GG525 LIFO queues, you get complicated equations. A lot of times they're not solvable. So best to keep it simple. All right, what are some of the types of queues? Well, what we're going to focus on is this one right here. Here are 4 of the basic ones. And it turns out that this is the one that you want to focus on. When you're designing queues, it turns out that it's best to have a single line of entry where only at the very end you branch out into multiple servers. That a multiple queue with single servers in parallel, that this is a bad design. It's bad to design 2 lines each for this single server. You end up tending to increase the amount of time that people spend in line. So this design is good. You'll notice it's just really a general, this is really a specific case of this guy. And for this one, we can do a series of these multiple servers, queues. So by mastering an MM5 queue or an MM6 queue or an MMN queue, which is what we're going to do, you'll be able to handle a wide variety of problems. Okay, so to do this, we use something called QTP Queuing Tool Pack add-in, and I'll just show you how to do it. Here it is in the notes, where to find it. Right there, you can find it. It is from the University of Alberta Business School. Check this out; it's been pretty stable. So you might want to use it. It's got a lot of nice functions in there. Okay, let's do an example of bank lines, and I'll show you how to use the queuing tool pack. I've set up a spreadsheet so that you can actually do it very quickly and easily. Okay, the first thing we'll want to note is that the spreadsheet is called MMS, Queuing Model MMS, and it uses the QTP function. So here's the setting. We have a bank with 2 equally efficient tellers. Okay, so that's the number of servers, yeah? Who are capable of serving 1 customer per minute. Okay, that's my service pattern. Oh, and it says it's exponential. Good thing, because that's what we're using. And it says here also 200 customers arrived during the peak 2 hours of lunchtime, and the lobby holds 25 people. So just to quickly write that, we have an M, because it's exponential, exponential. We have an M, 2, 25, Q. We're going to assume it's FIFO. Okay, so that's the notation. You don't have to know that, but if you do, it makes it a little bit easier to write. So let's go through, and we're going to calculate, for example, what's the average number of people who are waiting in line during that time period? What is our server utilization? How, for these 2 tellers, how often are they working and how often are they relaxing? What's the average time someone stands in line? And what's the probability that somebody waits more than 3 minutes in line? So those are all pretty cool questions we can answer very directly. So let's go to it. I've got my MMS spreadsheet in here, and you'll notice that I've got the QTP spreadsheet open. I'm going to not put it in for just a moment, but you'll have to, if you've downloaded this, and like I said, it's there, now that I've unloaded, I'm going to try loading it again. If you don't find it on your list, you'll have to browse and go to where you stored it. For example, I have stored it on my lecture data files right there. And if you click the OK, then it'll be in there. It says it already exists in there, and do you want to replace it? I said yes, so go ahead and do that. And once you do, you will see QTP macros go up there. It has a great help function where it will tell you the list of functions, and it even has a nice tutorial. Okay, so let's go through how to use this spreadsheet, though. Once you get Queuing Tool Pack, it'll be all there. It is for an MM, it says it up here, that this works for an MMS plus C queue model. MMS means exponential arrival, exponential service pattern, S servers, so we can handle up to whatever servers. If you have 20 or 30 or 40 or whatever servers, it'll handle it. and it handles the queuing capacity, so it handles the amount of time or the amount of the size of the lobby as well. So let's go back to our example. For all the things that are blue, so we have blue, we have white, we have green cells, and then we have, blue, yellow, and green, and then there's some white cells too. The blue are the things that you absolutely have to put in. The yellow are the things that you'll want to put in to handle your specific area. And then the green are the results, and the white are things like calculations that are in between. Okay? So that's what's going on here. And what we can do is we can actually look at, here's a probability of having a specific number. This is my histogram, if you will, of the number of items that are in the queue. All right, let's go through and put this in. You'll notice there are some comments as well. All right, so in our project, we had first of all, let's get the arrival time. If we're doing the arrival pattern first, we need to get that. So we had 200 customers in 2 hours, and that tells me that's 100 per hour. Okay, so we enter it over here, and it comes out over here. Second thing, we need to enter in the service rate, which is right here, and the service rate was 1 minute per customer, right? So we could do 1 minute per customer. All right, so there we go. So and this puts it into 60 seconds, you'll notice. Okay, and then the third thing is how many servers did we have? We had 2 bank tellers, and then it said that the queue capacity was 25. 25 people could fit in the lobby. So that's it. Okay, so let's see. Let's go down here. Here's what it says the utilization is. So each one of these tellers was working 83% of the time. Average number of people that were waiting in line is 3.61. So typically there were 3 or 4 people that were in line. And here's the average time that they waited. The average time that they waited was 2.17 minutes. Okay, I think that pretty much covers what we were talking about. All right. And then finally, well, what's the probability that somebody will wait more than 3 minutes? Well, we could come down here and look at the histogram and say, for example, let me put this in here. We could mentally add up all of these items right here, everything above 3, right? There's 1, there's 2, there's 3. So all of these things right here, right? Or there's a quicker way of doing this, and that is to come over here and put in a wait time criterion. So here we could put in, if we put in 3 minutes, it'll actually tell us the probability, the percent that actually meet less than or equal to 3 minutes. And there it is. It says that 72% wait less than or equal to 3 minutes. So that would mean that roughly 28%, 28% would be waiting more than 3 minutes. Pretty simple, right? There's lots of other queue things in the room. Probability of having an empty system is almost 10%. Probability of having to wait at all is 3/4 and 76%. Probability that you have a full system is darn near 0. So that's pretty interesting. A full system means that the buckets are all filled up. Now watch what would happen if we lower this to say 5. All of a sudden we'll have a probability, like if we made the lobby really small, all of a sudden we will have a probability that we have a full system. See that? Okay. All right. Let's go ahead and go to the last question in there, and we'll handle maybe. I'm going to just do a very clean one. Start it up again. What happened there? Let's try that again. Oh, I see. There we go. Okay. And let's go to, and by the way, all this is given in the slides. But let's do this one right here. So here we have a customer service center hotline for healthcare insurance, and what they've got is they've got people call in at 150 per hour during normal business hours, and we have CSRs that take an average of 360 seconds to service the calls. And here's interesting, they give a performance guarantee on their customers that says they will service their calls 95% of the time within 5 minutes. That's pretty similar. That's pretty common. So what we're going to do is suppose that a manager said, hey, should we staff this with 10 CSRs? Let's see if that makes sense. Right? It's a nice design thing. Does the capacity make any sense? So our job is to advise management, and one of the things that we can do is we can use queuing theory and our queuing spreadsheet to help us advise management. Okay, so let's do that first. So clear that out. All right, so let's go ahead and do that in our spreadsheet. Here we are in the spreadsheet. So we had 150 customers per hour, and it said we could service a customer in 360 seconds. So that is 6 minutes per customer. Now notice I've got to put it in the right. Number. Now, one person asked the question, well, doesn't this underestimate because this is just an average? It turns out that it assumes that it's an exponential. So there's an exponential assumption here. It's not. It doesn't under or overestimate. There's an assumption that the distribution is exponential. If you'll remember from your distribution studies, the exponential distribution only needs one parameter, and that's the mean. Okay. So we're putting the mean arrival rate. We're putting the mean service time as well. So we'll put in our postulated 10 servers. The queue capacity here, no, it didn't say, right? So this is like the number of people that can call. I don't know what would be the right one. Maybe we'd put it up to 100. Maybe we'd put it up to 1,000. There's going to be a number of people that can be put on hold. So let's put it up to, I don't know, let's put it up to, say, 1,000. Now, I'm not sure that a lot of people would wait on hold for that, but there you go. And, you know, if you put 25 or something like that, then that limits, that would mean that occasionally people are starting to hang up. They're not waiting, and so forth. And you can kind of adjust that based on your experience, and I'll show you how. Let's put it at 1,000, just to give you an idea. And we said we had a performance guarantee where we wanted to look at 95% of the people doing it within 5 minutes. Well, here's the first point that we want to make is that, now I put in my wait time criterion, and I want that to be 95. Okay. So it says right here, first of all, it says that the optimal number of servers is 18. What that means is that if I put 18 servers, then I'll meet this criterion, or I should expect to meet that criterion, and it's the minimum number that actually meets that. So just for fun, let's put that in, and let's put in 18. So that might be my first cut to say, well, if we really want to have 95% of the people waiting service within 5 minutes, we ought to have 18 servers. Well, if we do that, now this is interesting because we're getting the same utilization that we had before, 83%. That's just a coincidence, not anything cosmic about that. That would mean that we have 83% utilization. Okay, average number of people that are in the system, or average number of people in the queue is 2. So average number of people waiting in line is 2, waiting for these 18 CSRs. And average time they wait is a little bit less than a minute, 3/4 of a minute. Okay? So that would be it. Now here's what I wanted to tell you is that one way that you could deal with that would be to say, well, let's put in a small, let's go back to our small number, I mean the queue capacity. Let's put in a small number over here, and let's adjust the queue capacity for the amount of time that we actually observe that people do wait. It says here that if we have 1,000, a queue capacity of 1,000, people wait 598 minutes. Well, no, we observed nobody waits that long. So maybe you adjust this to see, well, what is sort of the maximum time that people do wait? And suppose the maximum time that they waited was, say, 20 minutes. Well, let's put in, say, 25. And you see that they're waiting typically 13 minutes. So clearly that's not enough. And so forth. So maybe you could adjust this to, say, 30 or something like that, 35. And that's getting pretty close to, well, this is the average time that people wait. So maybe 25 is a good number to say, yeah, the most that somebody will wait is that. And, you know, this would be a pretty unacceptable queue. But that might help you understand, like, sort of how big that queue really is. Let's go back to just making an infinite queue and putting in our optimal number of servers. So we found that 18 satisfies this 95% criterion. If we go to 17, you'll see that it's not satisfied. People are waiting a little bit longer, and so forth. So that might be the next question would be, and in fact it is in there, is to say, suppose they were able to renegotiate their staff performance guarantee to say that 90% of the time people wait 10 minutes or less. How could we re-advise? Very simple. Put in a 10 there, put in a 90% there, and this says we could do it with 17 servers. So let's go ahead and do that. What would happen if we went to 16 servers? Well, here's what we lose. 86% of the time, we're going to be within 10 minutes, and so forth. So you can see it really gives you a lot of scope and a lot of flexibility to be able to play with these numbers, to be able to design and calculate what are the right capacities that we need for staffing various queues, from everything from handling QA to handling customers calling at a hotline, to handling buses being washed, and so forth. Anyway, I hope you found this illuminating and helpful. Let's just kind of summarize this for a moment. What did we cover? Well, what we covered is really the fundamental aspects of queuing problems, right? And if you'll remember, for queues, careful how your language is there, for queues, what's fundamental is the arrival rate, the arrival. Let me change the color of the pen here. Let's go to blue. The arrival. You know what? I don't like this pen. I like this pen better. Okay, so hopefully we learned that the key things are the arrival pattern, right? The service pattern, the number of servers, and let's see, the size of the lobby, or we call it the capacity, and finally the queue discipline. And usually we said that this was exponential, that this is any number, right? This is an integer. I have 2 or 3 or 5 servers. This tells me how big the lobby is, and this is usually first in, first out. And that we call this M, and we call this M. And so when we do M, M, S, C, that's the number of servers, and that's the capacity. MMSC queues really can help you understand very quickly what are the different trade-offs that you have when designing capacity models for queues. So that's it. And hopefully you can use that QT tool pack in combination with that spreadsheet to solve a lot of things very simply. Very cool. And once you get used to it, hopefully you'll take to it like a duck to water. It doesn't take that much. Just a little bit of practice. Practice the problems that are in there. All right, take care. As always, if you have any questions, it's it's MZABEL @straightline ps.com. All right. See you later.